Hi boys and girls, this video comprises the lecture for section 9.7 Taylor Polynomials and Approximations, which begins on page 648. What is a polynomial approximation? Why are we interested in these things? Well, notice it says that polynomial functions can be used as approximation of other elementary functions. We might wonder why this is something we would need, why it would be something we're interested in. But you have always seen functions that are kind of neatly categorized for you. Perhaps you're studying polynomial functions, then rational functions, perhaps exponential functions, trigonometric functions. But out in the real world, functions are not so neat and organized. What if you had a function like, let's say, cosine of x plus arctan of something over the square root of e to the x times the natural log of 4x to the 67th power, and imagine you're trying to graph that or get information about that in some way. It would be very difficult. Functions can be very difficult to deal with if they're not just neatly categorized or organized into what you have ordinarily seen. So it becomes convenient or handy to come up with a function that is very similar to this complicated odd function and approximate the function by using polynomials. It's pretty amazing that we can do this actually. To find a polynomial function p that approximates another function f, begin by choosing a number c in the domain of f at which f and p have the same value. That is, p of c, the polynomial approximation function that you are finding or creating, is going to equal f of c. This little diagram illustrates it here. If we choose some c on our original function, which is the darker line here, and of course over here we've got the f of c value, the function value at that particular point. Pardon me one second. So as we look at this diagram, notice this is our original function, f, and we're going to begin to create this polynomial approximation function. We start with sort of nailing our approximation function to an actual point on the graph. In other words, we need to start somewhere, and so if we pick this point C at which we're going to begin to build our approximation, then we would say the approximating polynomial is said to be expanded about C or centered at C. Geometrically, the requirement that p of c equals f of c means that the graph of p, the polynomial function we're creating, passes through the point c f of c. Now notice here, if I decided that I was going to create a polynomial approximation function where the only requirement is that it goes through that point, that would really be a horizontal line, wouldn't it? Going through that point. That horizontal line, we could say, is y equals whatever that value is, f of c, right? And so that's not a very good approximation. If I let this be, I'll turn it to pink so you can see that it's different from the regular line. If I said, well, hey, I have an approximation polynomial. It has the same value at c that my original function does. Isn't that a pretty good approximation? And all of you looking at this video are saying, no, it's not a pretty good approximation. It matches only at that one point. How is that a good approximation? Well, it's a good approximation there, but I'll bet we can improve the approximation by now saying, what if, in addition to saying that the function I create has the same function value at c, what if I also say, let's let it have the same slope there as the function has there? So in addition to the requirement that my polynomial function that I'm creating have the same value at c that the function has at c, what if I also say that the slope of the polynomial function that I'm creating has the same slope as the function at c? Now you'll notice that we have this function, which is the line that's drawn here. And we've created a simple linear approximation where the line that we've created, supposedly, I guess, a polynomial approximation to the original function has met two requirements. It has the same function value at c, the place that we've chosen on the function to start building our polynomial approximation, and it has the same slope there. And so this p, the gray line that is drawn here, is a linear approximation polynomial. It's not that accurate. In fact, you can see that maybe say from here to here, in this range, you can see that the values are very similar. I might have overstated my case a little bit. The values are similar in that area, but the further away we get from C, you can see that the functions diverge and become very different from each other. I wonder how we could make our approximation better. Be thinking about that question, boys and girls, as we continue to work through this slide. Notice there are many polynomials whose graphs pass through the point C, f of c. Your task is to find or create a polynomial whose graph resembles the graph of f near this point, which we've done, and even the line that we've drawn, yes, it does resemble the graph of f at that point. One way to do this is impose the additional requirement that the slope of the polynomial function be the same as the slope of the graph of f at the point c, f of c, which we've discussed before. Thus, we'd want p prime of c to equal f prime of c. With these two requirements, you obtain a simple linear approximation. Now, did you answer that question I asked earlier? How could we make our approximation polynomial a little bit better? Well, keep thinking about that, because first we're going to do an example. Let's find a first-degree polynomial approximation of the function f of x equals e to the x power. Remember that a linear function or first-degree polynomial is a line, and generally we have something like y equals mx plus b. Here is the first-degree variable term. There will be a coefficient, which is the slope, and then of course we usually call this the y-intercept. But for this particular scenario, our a sub 0 should be the function value at that particular spot where we're creating our polynomial. In this case, it's going to be the function value at 0, because we're centering our polynomial approximation at 0. That's where we're going to start building this function. So our a sub 0 will be the requirement that the function value there at 0 match in the polynomial that we're building. Now a sub 1 is going to be the slope at that particular point, which will be the first derivative of our function at 0, and that will be the slope of the line that we're drawing. So now that we know where these coefficients are coming from, a sub 0 is the function value at the point that we're centering it at, and a sub 1 is the slope there. Let's build our function. We're going to need to know what the function value is at that point, and our function, fortunately, is a nice easy one to deal with, e to the x. So what is f of 0? Of course, that's e to the 0, which is 1. Fortunately, the first derivative, again, our friendly little exponential function here. And so when we find the slope, we find at 0, we find that it is also e to the 0, which is 1. So what we've identified is a sub 0 and a sub 1 for our polynomial approximation, called a first degree because it has a first degree term in it. So p sub 1, meaning first degree polynomial approximation, of the function e to the x is going to be 1 plus 1x. Now, boys and girls, that's a simple line. Think for a moment about how exciting this is. We have found a polynomial approximation for y equals e to the x power, centered at 0, and the only two conditions we've imposed thus far is that the function value at 0 has to match and the slope has to match. And with those two conditions imposed, we have a range of values, let's say, where our polynomial approximation function and the original function are very close to each other. Now, I sound a little bit more excited than you're probably feeling, but there is a reason to be very excited about this, as we will continue to discuss. Now notice on this slide I brought the screenshot of the previous graph here for us to take a look at, our original function f of x equals e to the x, and a first degree linear approximation, or first degree polynomial approximation. First degree simply means it's going to be a line, of the function f of x equals e to the x. we see that at points near 0, 1, the graph of p sub 1 of x equals 1 plus x is reasonably close to the graph of f of x e to the x. Again, as I was explaining, there's a range of values at which our approximation is really close to the values of the original function. However, as you move away from 0, 1, the graphs move farther from each other and the accuracy of the approximation decreases. So once again, my question would be, how could we make it a better approximation? So far, we imposed two conditions. The function value at our target point matches and the slope at our target point matches. Did you guess the answer? Perhaps you did. To improve the approximation, you can impose yet another requirement, that the values of the second derivative of p and f agree when x equals 0. So in other words, boys and girls, not only are we saying, well, let's let the function value match at that point, let's also let the slope match at that point, let's let the second derivative match at that point. Notice that what you're doing is you're taking your line, and now by using the second derivative to make your approximation more accurate, you're bending it so that it fits the curve more closely than it did when it was a line. Because remember, second derivative is now going to determine concavity. And if you think about the pattern that we're going to discuss, successive derivatives, if we continue to impose conditions that successive derivatives match, then we'll be molding and shaping the curve to fit the original function, which is e to the x power. So with successive approximations, you're going to get even closer approximations of the original curve, and what I'm drawing here doesn't look anything like that, but just pretend like it is. And so to improve the approximation, as I said, another condition that we can impose is that the second derivative matches the polynomial p sub 2 of least degree that satisfies all three requirements. P sub 2 of 0 equals f of 0, the function values match. P sub 2 prime of 0 equals f prime of 0, the first derivatives match, and P sub 2 double prime of 0 equals f double prime of 0, the second derivatives match, will be this polynomial. Notice it's a quadratic. And so you can see that P2 is a better approximation of f than P1. If you continue this pattern requiring that values of P sub nx and its first n derivatives match those of f of x equals e to the x, the original function, at x equals 0, you obtain the following. This P sub n of x, this polynomial approximation, you can see the pattern up to the nth term is approximately equal to the function e to the x. Now, boys and girls, this is astounding. How is it that we're creating a polynomial with its chunky little monomial terms, stringing them all together, and getting an approximation for the exponential function? They're not even connected to each other. They're not even the same categories of functions. So it is pretty amazing that we're able to do this. So let's move on to the next example. Now for this example, I'm not really going to work it out. I just want to show you the result. It's on page 649. A third degree polynomial approximation for f of x equals e to the x is this. Now at this point in time, don't worry about how we created this polynomial because we will see that in just a moment. But if we are saying that, I just want you to look at the notation. P is commonly the variable that we use for polynomial approximation that we have created. 3 means that we have gone as far as having a third degree term. Remember, these are polynomials, so they're going to have x terms with varying degrees. And so if we've created a polynomial up to the point where we have an x cubed term, that's called P sub 3 of x. And what you were supposed to do in this example, which I'm not really making you do because I just put the table on here for you, is construct a table comparing the values of your approximation polynomial with the actual function e to the x for several values of x near 0. So that's what we've done here. Here's x, the values that we've chosen, -1, -0.2, -0.1, 0, 0.1, 0.2, 1. What are the actual values when we plug these into e to the x? What are the values when we plug these x values into our polynomial approximation? Well, let's start here at 0 because remember, we centered this approximation around 0. It doesn't have to be centered there, but that's what we chose for this example. Of course, we expect that the function values match exactly there. They should, because remember that e to the x and our polynomial approximation at 0 have the same function value, the same first derivative, the same second derivative, and the same third derivative because we have a third degree term here. So yes, the function values should be exactly the same. But look as you move 0.1 on either side of 0. Here is the actual function value for e to the x. Here is our polynomial approximation. It's pretty close, isn't it? Now when you think in terms of what do we need to use these numbers for, doesn't it make sense to you that it's logical that in many cases this approximation would be good enough for whatever we needed for the exponential function? Now you're thinking, why would I create an exponential function when I can just use my calculator and plug this into e to the x and get the answer? Because we're not talking about functions like e to the x, we're talking about more complex functions where calculating the value would not be as easy as just plugging it into your calculator. But a polynomial approximation is much easier to deal with. Now let's go a little further away. Let's go 0.2 on either side. Here's the e to the x value. Here's our polynomial approximation value. Still very close. Moving now 1 unit away. Here's our e to the x value. Here's our polynomial approximation value. Still kind of close, but you can see that that's probably not going to be as useful as perhaps adding additional terms. Imagine if we had a 4th degree term, a 5th degree term, a 6th degree term, and they're easy to generate when you know the pattern. And then the more terms that you have, the better these approximations would be as you stray from your center point, which is 0. Obviously, the closer you are to 0, the better the approximation is going to be. And also, the more terms that you have, the better your approximation is going to be. Now this brings us to the general category that we're discussing here, which are Taylor and Maclaurin polynomials. The polynomial approximation of f of x equals e to the x, given in example 2, is expanded about, we just chose a target point, c equals 0. For expansions about an arbitrary value of c, it is convenient to write the polynomial in this form. Notice you have some generic polynomial approximation function here, p sub n of x is equal to, there's your a sub 0 term, the function value matches, a sub 1, first derivative matches, but now it's times, instead of times x, x minus c. It's kind of like a horizontal shift. We've moved off of the y-axis to an arbitrary c value somewhere, so instead of it being x to the 1 power, it's x minus c to the 1 power. A sub 2, there's our second derivatives matching, and that will be the coefficient of x minus c quantities squared. So again, instead of x squared, since it's a horizontal shift off the y-axis, then you have x minus c, and then similarly for subsequent terms, third derivative matching, and then x minus c to the 3rd power, etc., out to the nth term. The following definitions allow you to find a polynomial approximation for any value of c. Memorize this, boys and girls. Must be memorized because guaranteed you will have a question like this on the exam. You want to know exactly how to put together a Taylor or Maclaurin polynomial without having to derive it or figure it out, and so just make sure that you have them memorized. If f has n derivatives at c, and this is the generic case where it's not necessarily at 0, then here's the polynomial expression, the polynomial approximation function that we would be developing. F of c, remember that's the function value at c, f prime of c times x minus c, f double prime of c over 2 factorial, and you could put this over 1 factorial if you wanted to have a pattern that is complete, plus it would be f triple prime of c over 3 factorial, plus the 4th derivative at c over 4 factorial, etc. This general term, continue to generate these general terms where you have some nth derivative of the function at c over that n factorial times, and that's the coefficient, times x minus c to the n power. That is called the nth Taylor polynomial for f at c. Now if c is 0, which is a special case of the Taylor polynomial, we have this function. It's a little easier to put together because we've got f of 0, we've got the first derivative at 0, and then x, instead of x minus c, since c is 0, we can just put x there. The second derivative at 0 over 2 factorial x squared, the third derivative at 0 over 3 factorial x cubed, and this is called the nth Maclaurin polynomial for f. So the Maclaurin polynomial is a special case of the Taylor polynomial where c is 0. Otherwise, it's exactly the same thing. Okay, where does this lead us? To an example where we are the lucky people who are going to find Taylor polynomials for the natural log function. Now, again, the natural log function has nothing to do with polynomials, and yet we are about to create a polynomial function, remember with those chunky little monomial terms, which is actually going to approximate this elegant function, the natural log function. It's pretty amazing. Notice that our c is at 1, so we're not going to be using a Maclaurin polynomial, we're going to be using a Taylor polynomial. And let me show you how we're going to set this up. To get started, I have put here for us the rubric for putting together a Taylor polynomial, as you can see. So for p sub 0, wait, my little tablet is rattling, it's bothering me. For p sub 0, let's change color for this. All I need is the f of c term, which in this case is going to be, since our function is natural log, I need the natural log of 1, which is 0. For p sub 1, I need the f of c term plus the first derivative term, which is f prime of c at x minus, times x minus c. And I'll fill those values in a moment. Let me just write out the expansion. For a polynomial including up to and including a second degree term, I will need the f of c term, plus I'll need the f prime of c times x minus c, plus I'll need the f double prime of c times x minus c quantity squared, and remember this is over 2 factorial. So for the third degree polynomial, I'm going to need f of c plus f prime of c times x minus c, plus I will need the second derivative, of course, and over 2 factorial times x minus c quantities squared, plus now the third degree. Now you can see that as we develop these polynomials, we're just adding one term each time. F triple prime of c over 3 factorial times x minus c quantity cubed, and then finally for p sub 4, I will need all of these, which I'll write as quickly as possible, and then you be thinking about what else I'm going to need. And then when it comes to that, I'm going to ask you what it is. X minus c quantity squared plus our triple prime term over 3 factorial of c times x minus c cubed, plus, what is it, boys and girls? That's right, the fourth derivative at c over 4 factorial times x minus c quantity to the 4th power. Wow. So we're going to need to find out essentially the function value at c, which we already did actually, the first derivative at c, the second derivative at c, the third derivative at c, the fourth derivative at c. So hold on one second while I get a different color. I think I can fit it on this slide. Let's use pink. So let's see what's happening with the first, second, third, and fourth derivatives of f of x equals natural log of x. So f of x equals natural log of x, that's the original function. F prime of x is equal to 1 over x. F double prime of x, now remember that's x to the negative 1, so taking the derivative is going to give us negative 1 over x squared. Now I'm going to move up here to do the third derivative of x. If this is negative x to the negative 2, this is going to be 2 over x cubed will be our third derivative. And then our fourth derivative put that in parentheses so it doesn't look like f to the fourth or something like that. If this is 2x to the negative 3, it's going to be negative 6 x to the negative 4, which is negative 6 over x to the 4 power. Okay, so in addition to knowing what these derivatives are, we need to know the function values, or plug in c and find out what these derivatives are at c, which is 1. So let me find a space and another color for that. Okay, I went to another page here so we would have more room. Now I'm going to find these values, of course, at c is 1. So we've already discovered, wait, I meant to get a different color. F of 1 is natural log of 1, which is 0. F prime of 1 is 1 over 1. You can refer to the functions over here, which is 1. F double prime of 1 is negative 1 over 1, which is negative 1. F triple prime of 1 is equal to 2 over 1, which is 2. And F fourth derivative at 1 is equal to negative 6 over 1, which is negative 6. Now these are the coefficients. That's these things right here. So it is time now to put together our polynomial. We're going to have, let's see, where am I going to be able to do it? First of all, p sub 0 is equal to 0. That's all we've got there. P sub 1 is going to be equal to 0 plus f prime of c, which is 1, times x minus c. Then P sub 2 is equal to 0 plus x minus c, and now we're going to need the second degree term, which is negative 1 over 2 factorial, and since that's negative 1 over 2 x minus c, we'll have minus 1/2 x minus c quantity squared. Now let's do the third one. We're going to have 0 plus x minus c minus 1/2 x minus c quantity squared, and now we need to add the third term, which is not written here, but it'll be f triple prime of c over 3 factorial times x minus c quantity cubed. So f triple prime of c was 2, and over 3 factorial, since 3 factorial is 6, that becomes 1/3 x minus 1 to the third power. And then the last term that we need to add is the fourth degree term, which is f to the fourth of c over 4 factorial x minus c to the fourth power. This has become kind of a messy problem, as you can see, but we're just going to keep going. We've got p sub 4 is equal to 0. We just add each term on as we increase the approximation polynomial, adding terms. Squared plus 1/3 x minus 1 quantity cubed, and then finally our last term was negative 6 over 4 factorial. 4 factorial is 24, so that becomes minus 1/4 x minus 1 to the fourth power. Now you may have noticed I should have had 1s in all of these places. 1s in all of those places where there are c's there. And that's it, boys and girls. That's our Taylor polynomial. R sub 0, 1, R sub 1, R sub 2, R sub 3, R sub 4, 1. Now look at this graph down here. We are looking at the P sub 1 approximation, which of course is just a linear approximation. Then here's our P sub 2. Look at the range of values. Increasing accuracy each time as we get higher and higher degree polynomials that approximate the function. So you can imagine if we could get an infinite number of terms out there, we would have a polynomial approximation that is exactly equal to the function that is the natural log of x. Okay, stay tuned. And that's the bell, boys and girls, but it's not the end of your video. Now I've got 2 more quick examples for you, and then we'll be done with this lecture. This is example 5 on page 652. We're going to find the Maclaurin polynomial polynomials for cosine of x. Now remember that Maclaurin simply means it is centered at 0, which gives us a simpler little arrangement. I did bring it here for us to look at. This is the expansion for the Maclaurin polynomial approximation series, and they ask us, notice, for p sub 0, p sub 2, p sub 4, p sub 6. Interesting that they don't ask us any odd values. Well, notice I have put a table up here for you to see why this is the case. If we take the first few derivatives up to the third derivative, we probably should take more after this. You see we get the derivative for a function is cosine, derivative negative sine, then the next derivative negative cosine, then back to sine again, and of course this just cycles through. The fourth derivative is going to be cosine. I'll take it out to the sixth derivative since we're going to need that term. And then the fifth derivative is going to be negative sine again. And the sixth derivative is going to be negative cosine of x. Okay, so those are the ones that we're going to need for our 6th degree polynomial approximation. Now notice I also put up here this information so we wouldn't have to figure out the values, but let me fill out the table here. The function value at the fourth derivative at 0 is going to be 1 again. So it's just repeating the values that we have here. The fifth derivative value at 0 is 0, and the sixth derivative value at 0 is negative 1. Now notice how for all of the odd derivatives, 1, 3, and 5, that the value is 0. Since these are coefficients of your terms, this is why we are only being asked to give even polynomial approximations, because since the odd terms have 0 coefficients, they're not going to be in our approximation. So let's look at starting with p sub 0. P sub 0 is simply f of 0, which f of 0 is 1. That's it. Now p sub 2 is going to be f of 0 plus f prime of 0x, which will show that that is going to be 0, and then f double prime of 0 over 2 factorial. Well, f double prime of 0 is negative 1, so this is going to be 1, our original term, and then let's just show that this is going to be 0, because the function value at the first derivative is 0, times x, which means we won't have to write it, and then we saw negative 1 over 2 factorial, which is 1/2, x squared, and so we probably wouldn't write that term, so this looks like 1 minus 1/2 x squared. Now let's look at p sub 4. We would have, and I'll just skip the odd terms now since we know that they're going to go to 0. I'd have 1 minus 1/2 x squared, and now I'm going to need the value of the fourth derivative at 0, which is 1, and it will look like this term, 4 and then x to the 4th power over 4 factorial. Since c is 0, there's no x minus c here. So since that value is 1, this will be plus 1 over 4 factorial. 4 factorial is 24. So 1/24 x to the 4th power. Now let's do the last one. P sub 6, 1 minus 1/2 x squared plus 1 over 24 x to the 4th. And then the sixth term, the value at 0 is negative 1. And of course that means we're going to have negative 1 over 6 factorial, which is 720. 1 over 720, x to the 6th power. There you have it. Now there's a little bit more to do with this problem, and I'll show you in just a moment. Do a little experiment here. Let's compare cosine of 0.1 to versus our polynomial approximation function at out to the 6th degree at 0.1. So I'm just going to use my calculator to get these values. If you plug in cosine of 1 or cosine of 0.1, you get, let's just write it all out here in all of its decimal glory, 0.99500416553. Now, wouldn't you know that the Maclaurin polynomial expansion out to the 6th degree gives you this value, 0.995004165. What do you think about that? Pretty darn close, isn't it, boys and girls? Close enough, right? I mean, if we were actually using this as something that we had to do with this number, the polynomial approximation is certainly as good as the value we get by plugging it into the original function. Go us! We did something amazing. Last example, boys and girls. Now let's do the same thing, but find a Taylor polynomial for sine x, expanded about c equals pi over 6. So now, here, once again, just for reference, I put the Taylor polynomial sort of template or rubric up there for us. In fact, I've already put the first few derivatives. We're finding the third one, so we only need to go down this far. And here are the values as well. So we're going to go ahead and just put together the third one. We know that it's going to be p sub 3 is going to be f of pi over 6. I'll just write it, expand it out in this way, plus f prime of pi over 6 times x minus pi over 6. I'm not going to make that same mistake again. Plus f double prime of pi over 6 over 2 factorial times x minus pi over 6 quantities squared, and then plus f triple prime of pi over 6 over 3 factorial times x minus pi over 6 to the third power. Okay, so again, you'll memorize this and it will become more clear as time goes on. Now I'm just going to plug in the values because I have them here, and I'm not going to try to simplify them with the factorials either. I'm just going to leave the factorials in the problem. We're going to have p of 3, then sub 3 is equal to 1/2. That's the function value at pi over 6. And then plus the coefficient here will be square root of 3 over 2 plus square root of 3 over 2 times x minus pi over 6. Then the coefficient is the second derivative here, negative 1/2. So minus 1/2. Now in the denominator I'm also going to put times 2 factorial, even though we know that that's really just times 2, but just to keep it consistent. Then x minus pi over 6 quantity squared. And then the third derivative is minus the square root of 3 over 2. Again, I'm going to write times 3 factorial here instead of working it all out, times x minus pi over 6 to the third power. And there it is. So just a few little things to remember, a few little things to calculate as you see, and you can get your answer. Notice this is the polynomial approximation function, and you can see sort of the range of values around pi over 6 for which it's very close. It looks like it's exactly the same function. And of course, with successive terms and successive derivatives, it gets to be an even better approximation. Now, I'm going to cover these next two examples, or the remainder, or the Lagrange form of the remainder, in another lecture or possibly in class, and these are examples 8 and 9, so I'm kind of skimming over these right now. And getting to our homework page. Now, this is not a bad word. Don't be an S triple prime T. Now, if you're thinking a bad word in your head, shame on you, boys and girls. What you should do is try to figure out, what is the name of S triple prime of T? What is the term for that? First person who figures it out and emails me the answer or messages me the answer on Edmodo or Facebook, I'm going to give you extra credit. Now, your homework assignment, we're going to have to leave off one of these problems. Let me just check really quickly because I'm not giving you the Lagrange thingy right now. So I think that's 49. I know you hoped for more, but that's the only one I'm going to cross off right now. Wait. No, I'm going to cross off 46 as well. How's that? And you're like, 43, take off 43. No, not doing it. All right, that's the end of this lecture. Great job listening, boys and girls. You were so quiet today. I love that about you. I'll be waiting to see who knows what S triple prime of T is. Bye.